6x squared is also a solution. But when I do C1 x squared and C2 6x squared, I'm really getting only one function out of that. So the idea of linear independence is to come up with a precise statement saying, why are x squared and 6x squared not really independent? They're kind of the same, while x squared and x squared log x are. Okay? They're quite different, and we want to make them precise. This is the idea of linear independence. Okay? We'll define what we mean by linear independence, and then we'll go on and actually come up with a test. Okay? Sometimes you can see it by inspection, sometimes it's much more subtle. Okay. Before I do that, okay, let's go back to some geometry. Suppose I'm a three-dimensional space, x, y, z, right? Everybody remembers that you introduced like unit vectors in there. If I have an arbitrary vector v, right, I can write it as xi plus yj plus zk. ijk, some books use different notation, are just unit vectors along the three axes, right? So to go to any point P over here, right, I just project, right? I go x along I, y along j, and z along k. Okay, and it comes out that those three vectors, I, j, k, suffice to locate any vector in 3 space. As a matter of fact, I need precisely 3, any less won't work. Suppose I just give I and j, right? When I take a linear combination of just I and j, the best I can do is get a vector in the xy plane, right? I don't have any z component if I keep the k out, okay? How about if I use the unit vectors I, j, k, and I plus j minus k? That's an overkill. You don't need it. There's only 3 degrees of freedom, okay? These are what are called linearly dependent. These are linearly independent. I, j, k, why are they independent? Because there's no way of writing one as a linear combination of the other two. When if I were to do like I, j, k, and I plus j minus k, clearly this third vector is 1 times that, plus 1 times that, minus 1 times that. And that's the whole idea between linear independence and dependence. And now we can extend that to functions as opposed to vectors, okay? And this will give us a precise definition of exactly what do we mean that one function is dependent upon the other or not dependent. So here's a definition, okay? Definition of linear, let's start with linearly dependent. Of linear dependence. Okay? It's going to be a little formal. It's going to look a little intimidating at first, but then when you see, when you go and we'll illustrate it, it's not really that complicated. Okay. So I'm going to start off with a set of functions. And since it has nothing to do really with, I shouldn't say it has nothing, but basically this is something that's not integrally connected to differential equations, much wider, I'll use a notation like f1 of x, f2 of x, just to indicate end functions, okay? So, let a set of functions, in our case, these functions actually will be solutions to differential equations, okay? But for the time being, let a set of functions, we'll do like that, f1 of x, comma, f2 of x, dot, 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 a finite number, f sub n of x, be defined on some interval ab. And 2x, 3x squared, log x, x cubed, secant x, okay? Just a set of n functions defined on some common interval ab. Okay. These functions are, or the set of functions, are linearly dependent, so let's be careful now what we're doing, linearly dependent. Okay, maybe you want to put a little line under that, so we're defining linearly dependent. If there exists, or exist, right, constants, let's call them C1, C2, down to C sub n, and here's the critical point, not all 0. Okay? such that C1 F1 of x plus C sub 2 F2 of x all the way down to what? I got Cn Fn of x is identically 0 on AB. Okay. See, if I look at the equation C1 F1 of x plus C2 F2 of x, that's Cn Fn of x equals 0, that always has a solution, but all the c's equal to 0, right? It's a trivial solution. If it comes out, okay, that you can find constants C1, C2 sub n, not all of which, some could be 0, but if you can find a set of c's, not all of which is 0, such that the linear combination goes to 0, then the functions are called linearly dependent in the interval. Let's try to kind of make sense of that. You know, why write the term linearly dependent? Okay? Okay, because now I've got constants C1, C2, Cn, not all 0, such that this linear combination goes to 0. This is identical. Okay? That's why I put equals. In other words, it goes to, it vanishes identically. It doesn't depend upon the value of x. Okay? Let's say, for argument's sake, that C1 is the guy that's non-zero, because my thing says that not all constants are 0. Suppose, for example, let's make it easy. C1 is not equal to 0. Keep the C1 F1 of x on the left and bring all the other stuff to the right-hand side. Then divide by C1. What do you have? You have F1 of x as a linear combination of F2, F3, Fn. And that's why it's called linearly dependent. Okay? So when you have a linearly dependent set of functions, this is the formal definition. And what amounts to equivalently is the fact that you can always express one of the functions as a linear combination of the others. Okay? That's what happened over here with the ijk, right? You can't express I in terms of j, you can't express I and j in terms of k, but once you go to the third guy, oh, this guy is a linear combination of the first three. Okay? And that happens with functions also, right? If I had x squared, x cubed, no way of writing x cubed as a multiple of x squared. But suppose that the first function was x squared, the next guy was x cubed, and the third guy was 6x cubed minus 5x squared. That set would be linearly dependent, because the third guy is a linear combination of the first two. You have questions?
Yeah. Well, so when we move our functions and constants over to the other side,
Yeah.
so whatever other non-zero constants remaining are what the first one is written as.
Yeah, yeah. Or you can put the zeros there also. It doesn't make a difference.
Yeah, because then it would just be 0.
Yeah, exactly. But the important thing basically is that you can find at least one of the c's not equal to 0. Okay, so I said let's make it C1 for argument's sake. Doesn't matter how you order them, right? And then you can see you can divide through, and the essential thing is now I've got one function in this set as a linear combination of the others, and that's why it's called linearly dependent. Okay, and what you also want to note about this is that, and I'll illustrate this with an example. It's very important. Is that when you talk about linear dependence of functions, you always have to associate with that with an interval, not just the functions, but the interval. And I'm giving you an example of, I'll give you a concrete set of functions where in one interval they're linearly independent, in another interval they're linearly dependent. Okay? You don't get that with these vectors, I, j, k, right? It's either they're dependent or independent. There's no such thing as an interval because they're not functions. But when you talk about linear dependence, independence of sets of functions, you always have to include an interval there. Otherwise, it's not precise. Okay. So again, let me just read this again because my handwriting is not the best. Okay. I define here what we mean by a set of functions being linearly dependent. So we have a set of functions, f1 of x, f2 of x, down to f sub n of x. They're defined as some interval a, b. Okay. Why do I say that? Because if you had the square root of 1 minus x squared, that's not defined when x is greater than 1, right? Okay. Okay. And then what happens basically is you look at the equation C1 F1 of x plus C2 F2 of x, Cn Fn of x, identically 0. Okay? Not 0 for certain values of x, but it just goes to 0 identically. Okay? If you can satisfy this equation by a set of c's, not all of which are 0, okay, at least one of them is non-zero, in general there'll be more than one, okay, then the functions are called linearly dependent. Okay? And, I won't write this down, if they're not linearly dependent, they're called linearly independent. Okay? Okay. So that's basically the gist of that. Okay. Let me, give you an example. The book talks about this, it's kind of, special case. Since we deal with second order equations, okay, it's kind of obvious about, let's degenerate this thing to n equal to 2 and see what happens. Suppose I have two functions, not just the case of general n equals 2. So that's C1 F1 plus C2 F2, right? So I now write C1 F1 of x plus C2 F2 of x is identically 0, some interval AB, okay? Suppose that they're linearly dependent. If they're linearly dependent, then they're just constancy. Okay, let's assume, if the set f1 of x, f2 of x, notice that a lot of people make the mistake, they say a function is linearly dependent. No, linear dependence or independence is a property of a set of functions, right? So if the set f1, f2 is linearly dependent in some interval, okay, what does that mean? We'll work this all out. Well, if they're linearly dependent, that means there's this constant C1, C2, not both equal to 0, such that that equation holds. Let's assume C1 is not equal to 0, okay? Then we can say that f1 of x is minus C2 over C1 times f2 of x. And then you say, wait a minute, what happens if C1 is equal to 0? Okay, then C2 is not equal to 0, and you can solve for f2 in terms of f1. So what this says basically is that in a special case of two functions, if these two functions are linearly dependent in an interval, one is just a multiple of the other. Okay, so that's, so when it comes to more than 2, you really need this more elaborate statement. But in the case of two functions, we can just say, they're linearly dependent. One is a multiple of the other. So therefore, something like x squared versus 6x squared, those are linearly dependent, right? Because that one is a multiple of the other. But if I had x squared and x cubed, no, right? X cubed is not a constant times x squared, so they're linearly independent, okay? So like I said, for cases of two functions, you can kind of look at them and say if they're dependent, because one would have to be a multiple of the other. When you get to differential equations of order 3 or greater, then you may have to go back to this more precise statement, or fundamental definition of linear dependence and independence. Okay, I think the last thing I want to do now is discuss why is this interval so important, okay? You would think that, like if you look at this example, there's no interval here, x squared, x, because x is defined everywhere, and x cubed is defined everywhere. But let me give you an example of two functions, okay? And we'll find out that in a certain interval, these two functions are dependent, while in another interval, they're linearly independent. Okay, see over here. Let's look at the following example. f1 of x is equal to x, and f2 of x is equal to the absolute value of x. Okay? We know how to graph those, right? f1 is just a straight line, so it's like this, right? That's your f1 of x, right? And f2 of x, I'll draw that in red. The absolute value of x. What does the absolute value of x look like? Okay? It coincides with this guy over here, but then it goes like this, right? That's your f2 of x. Okay. Okay. I think you just look at the graph, you can kind of see what the problem's going to be. Okay? Let's consider the following interval now. Let's look at the interval 0 less than x less than infinity. Okay? Or x greater than 0 to the right of the origin. Right? If you consider the interval for x greater than 0, then f1 of x is equal to x. And what's f2 of x? It's x, right? The absolute value of x equals x when x is positive, right? Obviously, those are duplicates. They're linearly dependent, right? So over here, we got linearly dependent, f1 and f2. Okay? Let's go now where x is negative. Minus infinity, less than x, less than 0. Let's go to that interval and see what happens. Okay? Well, f1 of x is always equal to x, right? And what's f2 of x? When x is negative, the absolute value of x is just negative x. Again, one is a multiple of the other, so over here, in this interval, they're linearly independent. But notice that both examples that I gave excluded the origin, right? One was x greater than 0, one was x less than 0. Yeah, Here they overlay, over here they're just reflections and negatives of each other. Now, let's consider the following interval. -1 less than x less than 1. Okay? There's no way in that interval that you can write f2 as a multiple of f1. Okay? It's obvious from the graph, right? So therefore, if you have any interval that includes the origin, over here, they're linearly independent. Okay? So this is a good example illustrating the fact that when you talk about linear independence and dependence, obviously the functions involved are critical, but in addition, the interval can make a difference. Okay? Everybody see that from this example? Okay? So, okay, I think we'll call this a little early because let me just think, yeah, I don't want to get into it. Let me kind of just give you motivation for what I'm going to talk about next week. Some type of test, you know. There's certain functions I can give you, yeah. You don't have to be any genius to figure out that those guys are linearly dependent because they're so simple, okay? But suppose we had a set of functions, you know, could be large in number, even small number, but they involve really esoteric trig functions or something like that. And it would be very difficult to see if they're linearly dependent or not by inspection, and even applying this definition would be kind of, you know, sometimes it happens a lot in mathematics is that you'll have a definition of a fundamental concept, but as far as computation goes or algorithms, it's never used in that sense. You know, it's not a useful tool to actually prove that it's independent, but it's a fundamental definition nonetheless. Let me just give you an example of the following functions. Okay, cosine squared x. Okay, let the second guy be sine squared x. Let the next guy be secant squared x, and let the next guy be tan squared x. Okay, so that's what? f1 of x, f2, f3, f4, 4 functions. Okay? And actually make something that's even more hideous, you know? Are those functions dependent or not? Okay, so they're linearly dependent on one interval, okay? If you start applying this definition, it becomes very intractable. You'd have c1 cos squared plus c2 sine squared plus c3 secant squared plus c4 tan squared equals 0, and then you have to figure out, does that have a non-trivial solution or not? Very difficult, okay? It comes out that these functions actually are linearly dependent, okay? Maybe you recall from your high school trigonometry, tan squared x plus 1 is equal